To Professor Hussein Sehitoglu. Professor Sehitoglu obtained his degree in mechanical engineering from the University of London, University of London, I don't know what is the name, and then he got his master and his PhD from University of Illinois in Urbana-Champaign. That is a very nice place in summertime, a little bit cold in winter time. And basically they have two seasons there, that is August and winter, and the winter is long, but it's actually, it has been ranked consistently, I guess, the best engineering school in the United States for many standards. It's a large engineering school. And he is professor of mechanical engineering. He is also the chairman of the department, the head of the department of mechanical engineering. And Hussein and I guess we were just talking, we met first time and we knew each other 20 years ago when we have a lot of hair. And then many things happened, we became senior, and then we just lost the hair, and then a few other things, I learned a few things. And he was visiting Spain, and he was so kind to drop by here, visit the department, visiting there as well, and give us a talk about some of the work covered by history.
Thank you very much. I think you haven't changed very much over the last 20 years.
Oh, thanks.
Once I became an administrator, I gained some weight, so I do know that. Thank you for coming. I'm going to talk about twinning stress in metals with consideration of first principles. I think I spelled this correctly. It's I, small I, big M, small DEA. Yeah. And the work is funded by the National Science Foundation in the United States. Mathematical and Physical Sciences Directorate. First, I will give an overview of the presentation. In metals, you get stacking faults, and I'll describe what stacking faults look like. And in transmission microscope, they look like these fringe bands or fringe patterns, and they are observed typically in materials with low stacking fault energy. Okay, things like stainless steels and some FCC metal, pure metals. And then deformation twins are formed from stacking faults, and deformation twins play an important role in deformation of many materials, in many metallic alloys. And this is the twin, and this is FCC material in this case, and these are slip bands. For example, the slip bands are impinging on the twin, and that affects the deformation behavior, the stress strain behavior. So these things are published over the last few years, over the last 10 years. Okay. First, I'd like to describe you the philosophy of the research. In engineering, we work at macro scale, structural level, and that's the domain of mechanical, aerospace, and civil engineers. In the micromechanics area, we look at smaller length scales like inclusions or precipitates, and we describe the deformation with deformation gradient tensors, for example. And of course, what leads to these deformations are shearing of the atoms at the nanoscale. And that's of the order of 5 nanometers. This is of the order of, it could be 0.1 millimeters, or it could be 1 millimeter. This is finite element analysis, for example, of a cylinder in a car or an automotive engine. And here the length scale is of the order of centimeters. And then even at smaller length scales, at the quantum scales, we are looking at density of electrons, etc. My talk today will primarily focus on, in this regime, in the nanomechanics regime leading to this area. So I will be talking about this domain here. And this structure, the multi-level microstructure, has been envisaged as early as 1722, where the deformation of metals is recognized as shearing of atoms, and then there are grain boundaries, and then there are voids potentially at grain boundaries that dictate material behavior, for example. And so it is interesting that this picture was available quite some time ago, but now we have the tools to be able to make some predictions. So I talk about stacking faults, I will talk about deformation twins, then I talk about using these ideas to design new materials. If we have predictive capabilities, if we develop capabilities, then we could make new materials. Before we cast them, before we spend a lot of money making these materials, we can predict their behavior in advance. So my primary purpose of my talk is to develop this mesoscale twinning stress model. Okay? Now, going back to the importance of deformation, if you look at pure metals, medium or high stacking fault energy metals like aluminum, you get stage 1 deformation. This is typically considered single slip. Stage 2 where slip bands interact, and stage 3 where you start getting cross slip, you start getting a little softening. Okay, that's the typical stress strain curve for a pure metal like aluminum, like nickel, with a medium to high stacking fault energy. Now, if you look at a low stacking fault energy metal like silver, lead, it looks like this. Stage 1, again, present. Stage 2, where the slope is higher. And then, at some critical value of stress, when you reach that value, you initiate twinning in these materials. And then you get, of course, twin slip interactions. So twin slip interactions or twin-twin interactions. And as you note here, you get the onset of twinning here. And then instead of this decrease in slope, you could get a higher slope. So you could design some materials which give you enhanced properties. And Hatfield steel, one of those steels that I work with, actually shows upward curvature. The stress strain curve is like this because of the slip twin interactions. Now, these are all pure metals. If you look at alloys, in the alloys, they are already strengthened, so they don't start at a low yield stress, they start at a higher stress. So you might initiate, or you will initiate twinning right from the beginning. So you will get twinning, and this is the upward curvature that I was talking about. So there's twin slip interaction going on here, and this is a very desirable property. But after a while, of course, you will get some linear hardening and then more or less parabolic hardening. So these are some nitrogen steels that are very important. Hatfield steels, some of the austenitic steels exhibit this behavior. Again, polycrystalline material has grains. The slip traces look like that. Twin has a volume associated with it, so you could measure the twin volume fraction or things like that. Typically in materials that do not twin, you get in medium to high stacking fault energy materials, you get dislocation cells because things can cross slip and you form these three-dimensional structures. In materials that are low stacking fault, you get more planar structures, and that would be this material, the red one, or the blue one, for example. This is again the ones with low stacking fault energy materials. These are stacking faults. Now you might ask, so what's the purpose of your research? One of the things that we are interested in is the following. A number of you are working on crystal plasticity, or you are working on developing constitutive models, right? So in these models, what we do is we have to conduct experiments, and we have to establish, for example, yield stress from these experiments. The question that we are asking is, can we predict this yield stress, or can we predict the twinning stress from first principles? In other words, without making any, doing any experiments, or without making any assumptions. Now, clearly, that would be the twinning stress in this case. So this is stress, this is strain. There are two purposes to this slide. One is to show you that experimentally we can determine the twinning stress. You have to make the alloy. This is an iron, manganese, carbon. This is the Hatfield steel. It's oriented in a certain way. It's a single crystal oriented 1-1-1 orientation. It's pulled in tension. In that orientation, twinning is favorable. Okay, and so you get onset of twinning here, and then the more twin bands, and then the twins grow. Now, if you made measurements at a global scale, like with a large extensometer, you'll get the red one. So if you look at even with a small extensometer, if you're looking at an area which is large like this, you'll get the red curve. If you're looking at a smaller area, at a higher magnification, for example, you'll see that the onset of twinning starts at a much lower stress, right? But the deviation starts really here. If you're looking, this is digital image correlation area 2, which is right on the, encompassing that twin. So the two purposes of this diagram is to show that, if you want to measure experimentally twinning stress, you may have to look at fine scales, in your strain measurements, number one. Number two, ideally you want to be able to predict this from first principles, and some of this is published work. So I say here, twinning nucleation is currently obtained from experiments. A theory to obtain this quantity from first principles for metals and alloys is needed. It would be useful. It doesn't exist at the moment. Now, of course, we are interested in these twinning nucleation and then twinning propagation as well, because the twinning propagation dictates the slope of the stress strain curve, for example. One of the things we have been working on, we're working on two things. The first thing, this calculation of the twinning stress, we've been working on for the last 4 or 5 years, okay? And the second thing, we've been working on digital image correlation for the last 4 or 5 years as well. And we're trying to push digital image correlation to very small regions or high magnifications. So if you look here, the strain here at this scale in that twin is of the order of 10%, okay? But we know that in this alloy, the twinning strain is of the order of 35% or so. So if you take this, the scale barrier here is 15 microns. So what's happening here is you're using multiple lenses here. So one at a global scale, another one at a very local scale. You are trying to establish the twinning strain as well, and you are trying to really identify how the twin grows. And so this is basically the idea behind digital image correlation. You put speckle patterns. It's not very easy to get accurate results. You have to really perfect this technique, but especially if you're looking at higher magnifications, the speckle pattern moves from here to here. You can track the display, the motion, the position, and you can get the displacement gradients, and you can get higher gradients as well if you are interested in those. But from the gradients you can define strains, of course, and these are the strains here. And here, if you look at it at a high magnification at 15 micron bar here, the strains here are 30% and over. Okay, so I go to the theoretical part. The talk I'm going to give today is on the determination of twinning stress. You are all familiar that plastic deformation is due to slip, and slip occurs by motion of dislocation. This is a textbook figure shown here, taken from Callister. This is an edge dislocation. You apply shear here. It moves from left to right, and then it emanates at the surface, forms a slip step. So this is the motion of a perfect dislocation, okay, under shear. Now, in FCC materials, FCC metals, the motion of the dislocations are via the motion of partials, okay, not perfect dislocations, but these are the partials here. B1, B2 are the partials. And then there is this intrinsic stacking fault in between. So the motion of the dislocations would be the motion of this entire fault. And the width here is, I'll come to that. That's the stacking fault width. If you have a low stacking fault energy material, that width is pretty wide. That's pretty wide. If you have a high stacking fault energy material, it's pretty narrow. That way the partials can combine and you can get cross slip. So it's important to note that the FCC stacking is ABC, ABC. Within the fault, the stacking is a hexagonal close pack. So in this case it's ACA, and then once the trailing partial passes, you recover. If you look at a point, material point, you recover in the slip state, you recover the ABC stacking again. But within the fault, the stacking is not a face-centered cubic stacking. Okay, now I guess the question is, what are the energies involved when the atoms move? Okay, so this is the ABC stacking for a face-centered cubic material. This is 1, 1, 1 direction. That's this. So this would be the slip plane here. Okay, and 1, 1, 2 bar direction would be the direction of the partial dislocation. Okay, and if you move let's say this is your slip plane, and if you move the blue atom by half a Burger's vector from left to the right, okay, and then move the green one also, if you plot the energy versus displacement in the 1, 1, 2 direction, you reach a peak that's called the unstable stacking fault energy. So that position is an unstable position. It doesn't want to stay there, and it requires energy to get up that far. So that would be when the blue is right in the middle here, the green is right in the middle there, okay, and you move everything on top here. You know, this is I'm trying to push a partial dislocation through, but this is not quite a partial dislocation, entire partial dislocation motion yet. So here this moves here again, so you get this configuration which corresponds to a highly energetically unfavorable state. Now if you move further, if you move these atoms another half a Burger's vector, then you have moved the blue atom into the green position, which is here, and then you have moved the green atom to the red position here, and that is a metastable position. That motion of the atom creates an AC stacking, and that is the stacking fault. Okay, that's what we mean by stacking fault. So this is the ABC stacking of the face-centered cubic. material. So here, this is a one-layer fault. Okay, this is a one-layer fault because you get AC, and then from then on you get again ABC stacking. In that position you are in S, and the energy associated with that metastable position is called the intrinsic stacking fault, and this stacking fault energy. This is available in textbooks. It has been measured, and even elementary dislocation books, they quote you values for these things. Now, if you decide to move the atoms further by making atoms again move from left to the right, if you try to move it further this way, and then you get this AA stacking. That's a highly unfavorable situation. It will not happen because the energy barrier associated with that is very large, and that's called the gamma max. So what you do is you go here, but you wouldn't necessarily go through gamma max. Okay, now this idea, this is called the generalized stacking fault energy, first introduced by Vitek in 1968. And if you plot this in 3 dimensions, if you do the calculations in 3 dimensions, this is the path that we just investigated, okay? So that's gamma US. By the way, this is first, the term unstable stacking fault energy is coined by Rice in 1992, associated with this point. This is intrinsic stacking fault. It has implications in slip, it has implications in fracture and all these things as well. But I'm not going to talk about those. But this would be the energy barrier if you moved a full dislocation, a perfect dislocation. You could see the energy barrier associated with that is quite large. That's why in FCC metals, the partials form, and you get the motion of the partials rather than the full dislocations. That would be the motion along 110 direction, which is what we teach our students in elementary dislocations or elementary material science. This is again all 111 plane. That's 110 direction. This will be the 112 direction. So that's the gamma. This is the gamma curve. And that's the motion I just described. Energy for stacking fault formation during passage of a Shockley partial is area under this surface. Okay, really area under that surface. I'll come back to that. So I talked about this a little bit. Now I would like to tell you that when we do these calculations, we take periodic boundary conditions, and we create a stacking fault by passage of a Shockley partial, and the stacking fault energy is the energy of the intrinsic stacking fault minus the energy of the ground state FCC divided by the area on the fault plane 111, and that's the definition of ISF. Now, twinning. What happens? We looked at the first stages here. What we did was we went this far. We went to formation of intrinsic stacking fault, and we went through this curve up to this point. What happens if I now move the entire row of atoms above this plane, again from left to right, okay, by a Burger's vector BP, okay? So then what would happen is that if I pass another partial dislocation in the 112 direction, then I would be moving this fault one plane up, which is what happens here, okay? So in this case, I move another partial on this plane, and the plane moves up now, the fault plane. And then if I move all the atoms by another Burger's vector above this fault plane, then I move that plane up by one more layer. And this is the final, for example, if I do this in the sequence that I describe, I will form a 3-layer twin. So what's happening here, as you note here, is that this is the FCC, and that's a twin boundary, and that's a twin boundary, and this is the twin. So I can create a twin in this fashion. So, and you could see here on the twin plane, this is the B, and this, there's symmetry along that plane. This is the A, that's the A, and that's B, and it is C and C on the side. And the way it's done is you move the entire row of atoms on top of this layer by BP, and then the next one you move this entire layer of atoms above this plane by BP this way. So you can create larger layers of twin. And then if you look at gamma versus displacement plot, we went through gamma US, gamma ISF, and then you go through another peak called gamma UT, and that's called the unstable twin energy. And then you go through a minimum which is called 2 gamma TSF, that's the twin stacking fault energy. And 2 times that's 2 gamma TSF is equal to gamma ISF for pure metals. Okay. So this is the formation of a twin by a successive motion or successive passage of partial dislocations on subsequent layers. Okay. Now, area under this curve is required energy to twin the lattice by successive shear. Looking at this for copper, for example, get this, you can see gamma US is here, gamma UT is different numbers, okay? But after a few layers, things stabilize reasonably well, okay? Okay, so this is for pure copper. These calculations are density functional theory calculations. This is published in APL. Fault energies converge after the third layer. This is for lead. Okay, it looks different. The numbers are definitely, the energy levels are definitely different. Okay. Also the pattern, the shape is different as well. So this would be twin nucleation, this would be twin growth. Okay. After the third layer, there's pretty much a convergence. Now, if you look at the results that we have, I plot here lead, silver, gold, copper, nickel, palladium, platinum, aluminum, right? These are the theoretical results for the energies. These are the experimental results. You cannot get an experiment for unstable value of the energy, okay? But for the intrinsic stacking fault, you can get the energies experimentally, and they are in excellent agreement with our calculations. For gamma UT, we have the theoretical results. You can't get experimental results. And then 2 TSF, there's also good agreement. Some of these experimental results are taken from the literature. The above table represents the most complete set of DFT-based theoretical calculations of fault energies for FCC metals. Note that there are some materials here, some metals here that are not known to twin as coarse grained materials, but we are including almost all pure metals here. Okay. Now, what has been done is by taking some of these gamma curves, you take the derivative of these gamma curves, and you can try to predict stresses, for example, for slipping or twinning. But that gives you very large stresses. So you take the energy curves, for example, you take derivative of these, or you calculate ideal shear stresses, gamma UT minus 2 gamma 2SF divided by pi B twin. B twin is this value here, okay? Characteristic length of the material, These ideal stresses would be very large, for aluminum and copper, and that's done by Ogata and Yip. Can we predict realistic twinning stresses? Because if you look at twinning stresses for these pure metals, they are of the order of megapascals, not gigapascals. Okay, this is gigapascals. So there are some simple models out there. I shouldn't say theories, but there are some simple models out there, and they go back to 1960s, and they all say the critical stress for twinning is proportional to gamma ISF, intrinsic stacking fault energy. There are some constants they have, theta, beta, k. These are constants. Of course, we're trying to determine without any constants. So these are the constants. And you could see as the stacking fault energy goes up, this model predicts the correct trends. The twin stress goes up. But it says that the twin energy, twin stress, is only a function of gamma ISF. But I just said that the entire energy curve should play a major role, not only the stable value. Need a more fundamental approach to predict twinning stress. So we have density functional theory, and then the twin occurs, a twin happens as a consequence of passage of partial dislocations. So there is a twin nucleus associated with that. And this twin nucleus has basically has dislocations bounding it, and this set of dislocations here are sessile. That means they are stationary. These three here are glacial, they move. So the way the twin will move is that you have these have both edge and screw components. This set of dislocations move. This twin nucleation has been observed as a three-layer twin with transmission electron microscope, and has also been postulated by Mahajan and Chin in 1973. What we have now is the following. We have a total energy, what we're saying, which is a combination of the elastic energy associated with these dislocations that bound the twin nucleus, work done by applied shear stress, which we know, and then the energy, we have to overcome the energy associated with the twin energy pathway. That's the generalized plane fault energy. So if we have this entire energy expression, we have a total energy expression. So the red is the energy contribution of edge components, blue energy contribution from screw components, and if you look at the terms here, there is a shear modulus here, but we determine that from our calculations. Berger's vectors, they're known. This is number of layers in the twin nucleus, which will be 3 in our model, and D is unknown. That's the twin length, if you like, or twin. This is the thickness. This is the twin width or twin length of the twin. That's D. So that's an unknown parameter. That's the applied work done due to applied stress, and that's GPFE, which is shown here. It's basically the integral of the generalized plane fault energy curves. And so you can write the total energy expression again. This is the GPFE expression. This is the applied stress, shear stress here. But we're going to try to minimize. We're going to minimize this and try to establish the twinning stress. Okay. For a stable twin configuration, we have to look for the minimum for this total energy expression. If you do that, you get this result, which looks a little complicated, but I'm going to simplify it, okay? But the important thing is this is the twinning stress. It is a function of gamma ISF, but it is also a function of gamma TSF, that's the twinning stacking fault energy. But moreover, it's a function of gamma UT, the peak, and it's also a function of gamma US, which is appearing in here. Note the signs here, and this will come into play here. These are the positive terms here, and there's some negative terms here. We can certainly determine from this calculation we can determine the equilibrium width of the twin as well. And for nickel versus lead, that D is different based on our calculation. But most importantly, we can simplify this expression, this complicated looking expression, and get the following result. The critical stress for twinning is equal to a term which has gamma ut, the unstable twin energy, and if that goes up, the twinning stress will go up. Now, ISF is appearing here, and ISF is appearing there. Actually, this term dominates this term. The ISF here is larger than that. So if you increase the intrinsic stacking fault, the twinning stress will also go up. And that's consistent with the Venable's model and what we teach our students, right, in the undergraduate classes and graduate classes. But that has a modifying effect. This is a dominating term, actually, it turns out. And the interesting is gamma US is also playing a role, and increase in gamma US will decrease the critical twinning stress. So increase in ISF or 2TSF, these two terms are almost equal, I said, right, will increase the critical twinning stress. The increase in gamma US will decrease the critical twinning. This opposes it. Okay, this is like a competition between slip and twin. Okay, slip and twin. So this is the critical stress for twinning. Of course, if this value is very large, because of these numbers being very large, you'll likely get, slip deformation. You will not get, but if this number is small, you'll get twinning deformation. Now, twinning stress depends non-monotonically on stacking fault energy. Now, we said that we taught our students that critical stress for twinning is proportional to gamma ISF, or some form of it. Maybe this has, in that expression from Venables, there's an exponent here. But nevertheless, this is what's been taught in textbooks, every textbook we have. But you could see that this correlation is not very good. It doesn't work. In fact, lead here, okay, has a higher ISF, but a lower twinning stress compared to silver, gold, copper. Okay, so these are the experimental ranges from the literature. There is a variation, and the red are the predictive values. Now, nickel, I didn't show any experimental results. Typically, for a regular coarse-grained nickel, you don't get twinning. Now, these are the entire results plotted versus gamma ut. What we're saying here, that twinning stress depends monotonically on unstable twin stacking fault energy, the gamma ut, that peak. There's a better correlation between critical stress and gamma ut. And the higher the gamma ut, the higher the twinning stress. Consistent with that equation, consistent with the experimental data here. Now, you could find some twinning stress results for aluminum these days. You can't put it here. But we looked at the old literature and primarily looked at our prediction. And the most important thing perhaps, is that these numbers are of the order of megapascals, not gigapascals. So you need to invoke continuum theory along with atomistic theory to be able to predict realistic values of applied stress, twinning stress. The summary of the results, as I said, the critical stress experimental values in the literature, there's quite a bit of range. That's why you might need digital image correlation to pin this thing down, because somebody uses one technique, the other one uses another technique. they might report very different values of twinning stress because they were not able to, if they used I don't know, position measurement or something like that instead of very fine resolution, they might get quite differences. But nevertheless, our predictions are right there. There are no constants used in this model. There are no fitting parameters, nothing. And these are the ideal values. These materials twin. These materials are known to cross-slip, so didn't provide experimental values here, although you can find some values. Okay. There are some other things that can be explained with this model, of course. Twinning is directional. Slip is bidirectional, so you can twin in only in one direction. You can't twin in the other direction. This is known. And this model, naturally shows you that. So I showed twinning in this direction, right? So this is the twin. That's the mirror plane. Can you twin in the other direction? Well, the final configuration is the same, right? And the gamma ISF is the same between here and here. But look at the peak. In this case, you are going through a gamma USF of the order of 2000. Here you're going through a gamma US of 200. So clearly, if you had a model just based on ISF, you would say that you could get twinning here because ISF here and ISF here are the same. What's different is the unstable, the gamma UTs. For that matter, gamma USs are different as well. But you cannot get twinning in that case because if you predicted the twinning stress by the same model, in that case, you'll get twinning stresses that are higher, 170, 310, 400, 370, few times, factor of 3 or 4, higher than in the 112 direction, 112 bar direction. There are some models out there that claim to say, okay, we have this magic parameter T. If look at the ratio of gamma US, gamma UT, it's in the right direction, but they would not be able to predict the fact that you could not get twinning in the anti-twinning direction because that T parameter is still larger than 1 in this case and larger than 1 in this case. So this kind of model will say I should get twinning here too and as well as here. So I wanted to point that out. So I'm not quite done, but I'm going to do an intermediate summary. Presented a hierarchical multi-scale adjustable parameter free, no free parameters for twin nucleation in FCC metals and alloys. I didn't do alloys yet. I'm going to do that next briefly. Predicted twinning stresses are in excellent agreement with available experimental data. It inherently accounts for directional nature of twinning. That means it twins in one direction, not in the other. Now, what do you do about the alloys? Now, ideally what you want to do is you want to be able to design new alloys, right? It becomes a little more complicated. So this is the green part here, materials design. This is copper aluminum alloys results, and aluminum is put 8.3% aluminum. These are aluminum atoms here. And then again, the same idea. You create a twin. And you look at the gamma curves. They are different. This is pure copper. And that's copper 5% aluminum. You could see the barriers have come down. So it should be, according to the model, it should be easier to twin the alloy compared to the pure metal, pure copper. Is that true? Yeah, it is true. So these are the numbers you get for the 5% and 8.3%. the gamma TSF, gamma UT goes down from 200, 179 to 176, but also gamma TSF goes down from 4032 to 11. And if you look at the results here for pure copper, 5% aluminum, 8.3% aluminum, these are again experiments and done by others, and the predictions, you could see that the alloy, 8.3% alloy, has a lower twinning stress compared to the pure copper. So a priori you wouldn't know that unless you do the calculations. So the idea is to use, again, this is plotted tau critical versus gamma UT, copper 5% aluminum, 8.3% aluminum. The idea is to extend the knowledge from pure metals to development of new alloys. Well, if you look at steels, like iron-based metals, we know that if you plot yield stress versus addition of alloying elements, right? It's again undergraduate information. Nitrogen is very effective as an interstitial in increasing the strength, and it is being used. So you keep adding nitrogen, strength goes up, it reaches a peak, starts to go down, and that peak corresponds to about 1% nitrogen. Can you explain these things? Well, or can you predict this without now a priori knowledge? You can, you know, experimentally, you know, the role of nitrogen is huge. You know, you get, this is true stress strain curve again, 1-1-1 orientation in tension. This is no nitrogen, this is with nitrogen. No wonder why this material is very attractive. But after a while, after you keep increasing the nitrogen, the strength goes down. Again, it can be explained based on some of these concepts. This material can twin, but it depends on the orientation that you pull in. This is again the stacking fault, right? I point out that that's the displacement associated with the partials. That's the stress, the shear stress, edge and the screw components. That's the internal elastic energy for the stacking fault, which you can calculate. Okay. And then the total energy in this case is elastic energy and misfit energy. I'm not doing twinning analysis. I'm just looking at the width of the fault. Can I predict the width of the fault in this case? Just pure fault width determination. Elastic energy associated with the fault. So the fault width is D here, okay? And D appears in my equations here. And then the misfit energy is again the integration of gamma, the gamma curve. But now there's no twin. You don't have to go through the entire three-layer twin formation. You're just going on only to formation of the intrinsic stacking fault. You again minimize this E. It's the same figure I showed before. So you do first iron, you add nitrogen, you get modified curves, of course, right? So if you do pure iron, it looks like this. This is FCC iron. If you keep adding nitrogen, this peak goes up. This level goes up as well. So if you keep adding nitrogen, the curve gets modified. Again, the same idea. So if we minimize the energy, we can get a closed form solution for the stacking fault width. And what happens is that that width, d, as a function of intrinsic stacking fault energy, we teach our students that if the intrinsic stacking fault is 0, right, the width should be infinity. Yes, that's what we should tell them. That's for a Volterra dislocation, goes to infinity. But that's not the case, because we have to look at the entire gamma curve. In fact, what happens is that if you do that, you keep increasing the nitrogen around 1% nitrogen weight percent, the separation width is maximum, and after that it starts decreasing again. So this corresponds to the highest strength point, so you can predict that as well. Again, no twinning in this case. This is my final slide. Stacking fault width is determined by gamma surface, not by intrinsic stacking fault energy alone, which is again what we teach our students. The models developed for twinning stress, which I focused on primarily in this talked briefly about stacking fault widths, can be utilized to design new alloys. Thank you.
Thanks for the nice talk, and we have time for just a couple of questions.
Yes.
Do you speak about twin migration? Do you think, that should be taken into account among the possibilities between sleep, twin formation, and once it exists, twin migration?
So in the twin migration, if you're looking at migration over long distances, for example, you'll hit other barriers. In the model I present, I don't have any external barriers to twin. In other words, I move the atoms, I create the twin, and I propagate the twin unhindered. That is migration, but no obstacles. So if you have obstacles like slip band, or another twin, a crossing twin, you have to do a different modifier analysis.
I was more talking about, the full twin.
Moving. No moving here. You're thinking of nanomaterials. Yeah, this is controversial. People have proposed twin bound, or grain boundary motion as a way of explaining. So a sigma 3 grain boundary is a twin boundary, same thing. Okay, so if you analyze nanomaterial and you analyze every grain boundary, you get a large percentage of sigma 3 boundaries. So they argue that the behavior of the deformation of a nanomaterial is by the motion of the grain boundary, right? It's plausible, but there are other factors playing. There are diffusional factors playing a role here, and there are some papers there, but no calculations.
Even just a twin within a grain. Like if you take, let's say, a graphite crystal, like a twin crossing, just having the twin moving inside would accommodate something.
That's what's happening here, though, essentially. The twin, when you say twin is moving, what's happening is, you have the upper twin plane and the below twin plane. Each plane can move. I just happen to keep the bottom one, fixed, and then by passing the partials, I move the twin up. If I put the partial in the other direction for the bottom plane, I'd be then growing the plane. I'd be growing the twin downwards. We have done those kind of calculations. It wouldn't make any difference in my result, you get the same result. But that would be essentially the growth of the twin in both directions, you know.
All the trailing following the...
Right. But the twin, if you mean by twin migration, this twin is translating from one location to another location. I'm not, I don't think, I'm not addressing that, nor do I have any evidence of that in mammals. Except if you have, I mean, you could have pure diffusion, but not at finite temperatures. Yes?
You have used these elements already.
Yes, yes, sir.
More or less 1 millimeter. What is the scale of the
Oh.
size?
It's a very good question. So the size there is like 100 microns by 100 microns in that image, right? This one.
Okay. At this scale, this is the pattern that you use for the digital image correlation. Is a natural pattern?
This pattern?
Yeah.
It's not a regular pattern. It depends on the magnification you want to look at. You put different size speckle pattern. You use a finer pattern for higher magnification experiments. You use a coarser pattern for lower magnification experiments.
Which one is the finer?
This particular image is just illustration, you know, just so to speak, for the technique. So this is a fairly coarse pattern. The ones used here are very fine, like, and how big are the speckles? Is that what you're asking? I think they are sub-microns, 0.03 microns, something like that. It's very small.
And you deposit this speckle?
We are doing it different ways. One is using actually a very airbrush, you know, just like in a, yeah. We are using it at high temperature, so we are using high temperature paint with small particles in it, things like that. So we're playing with a lot of things. Yeah. Yeah. So different sizes are being used depending on what features you want to look at, right? We are using it in like fracture mechanics, as I'm sure you are, depending on what we want to do. We are using, for crack tips, we're using very fine patterns.
Okay, thanks. Thank you very much.
Okay.